Hi everyone, in this video we're going to talk about extrema, which will push us towards our next applications, which we'll talk about in calculus, which are curve sketching and optimization. Yeah? So let's begin by recalling our favorite subject, foundations, right? Or algebra 2 or algebra 1, wherever you may have seen this. So let's recall. If we have a function, your favorite polynomial function, y equals ax squared plus bx plus c, yeah? Then this function, we recall, has a maximum or a minimum value, depending on if it's opening up or opening down, right? At x equals negative b divided by 2a. Yeah, and we remember this. This is kind of nice and helpful. And remember, if it's opening upward, we're going to have a minimum value, an absolutely minimum value, right? Here it is. And if it's opening downward, then that means that we'll have an absolute maximum value. Yeah. So the question that we came across in foundations, if you recall, is what happens if it's not quadratic? What if it's cubic? What if it's quartic, right? What about cubic functions? Yeah, quartics. What about trig functions? How can we find maximum values of functions that have sines and cosines and tangents? What about exponential functions? Logarithms, yeah? So we want to extend this idea of being able to find the maximum and minimum values of a function to any type of function that we like. And let's begin with our idea. Let's stare really hard at this picture. And we're experts in calculus now. What do you notice, calculus-wise, happens at the minimum value or the maximum value? Well, you see that there's a horizontal tangent line here. And that's kind of interesting, yeah? And that's not the only time that this is going to happen, but this will be a great clue for where these maximums and minimums are going to occur. So let's get right into it. These maximum and minimum values are going to be called extrema. Yeah, the extreme values of a function. So let's begin with the definition. A function f of x has a local maximum value. Has a local maximum at the point x equals c if f of c is bigger than or equal to f of x for all x near c. F of x has a local maximum at x equals c if f of c is bigger than everything near it. Okay? And let's look here. The little black dot here is larger, has a larger function value than all the other function values near it. Yeah? What does near mean? Near means on some open interval around c. Yeah, some open interval. So let's draw another picture just to see what could happen. Suppose you have maybe a function that wiggles. Yeah, maybe it has two humps like this. Then this point here is a local maximum because for some tiny little neighborhood, tiny little open interval around that point, the filled in dot up there is the biggest function value. Yeah? And this is just for some open interval. If you make the open interval larger, you'll go over here, but this one's its own king of its own little mountain, yeah? So a local maximum just means that there's some neighborhood, some little open interval, around which this point is the king of the mountain, yeah? What does it mean for f of x to have a local minimum? It has a local min. Well, nothing's going to change. The only thing that's going to change is that f of c will no longer be king of a mountain. It will be the smallest value for all x near C, yeah, on some open interval. This is what it means to be a local minimum or a local maximum. Again, it's either the king of the mountain, or if it's a local minimum, like you can see here, it's the smallest value around the point. Okay? And we'll draw some pictures, I promise. Let's define another type of extrema that we want. These are called absolute minimums and absolute maximums. Let's define that. F of x has an absolute maximum in some interval, call it I, at x equals c if, well, if it's a maximum, it better be the largest thing, right? If f of x is bigger, or sorry, I messed that up. If f of c is bigger than or equal to f of x for all x in the interval I. Okay, sorry this got a little messy here. F of x is the absolute maximum on an interval if the function value is the largest for all values in the interval, not just near the point C, but for every value in the desired interval. What do you think is going to change if we have f of x having an absolute minimum? Nothing else changes except, again, we don't want it to be the largest value. All that we need to change here is f of c is less than or equal to f of x, and everything else carries through. Yeah. So let's draw some pictures. Pictures really help, and they are indeed worth 1,000 words, so let's do an example. Let's draw your favorite function. Here's the point A, here's the point B, and suppose it looks something like this. Yeah, something like this. Where are the local minimums and local maximums, if any? As you can see, where do we have king of a mountain? We have a local maximum here, right? Where do we have a local minimum? We have a local minimum right here. It's the smallest value in some neighborhood. The points on the endpoints are not local minimums and maximums, because any open interval that you put around x equals b, for instance, will not be wholly contained in the interval. Okay? So really our only local max and local mins are at these 2 points that I've indicated. Yeah? So the point here is the x value of the local min. The point here is the x value of the local max. Where's the absolute minimum and absolute maximum value? Pause the video, see if you can put this together yourself. So we have an absolute minimum value. It looks like over here, right? This is our absolute minimum. It's the smallest function value on the entire interval. And here it looks like we have a local and an absolute maximum. Yeah. So this mound here gives us the local maximum because it's king of a mountain, but it's also the largest function value on the entire interval. Let's do another example. Here's A, here's B. So, pause the video, try to find the locations of the local minimums, local maximums, and the absolute min and absolute maxes. Give it a shot. Alright, so I see that my local min will be here because it's the smallest function value in a little open neighborhood around the point. Here is my local max. because it's the largest value around on a neighborhood around the point. My endpoints, again, are not local mins, but in this case, neither one of them are local maxes either. So in this case, this point is the local and the absolute maximum, because it gives you the largest function value on the entire interval. And the local minimum is also the absolute minimum. Yeah, so it's both. So what are the two locations we can see here of local minimums? Again, I see at my local mins and local max, I have horizontal tangent lines, right? But that's violated. That idea is violated here. What's the derivative at this corner point here? Or the derivative at this corner point? It doesn't exist, right? So keep that in the back of your mind. We're going to need some condition where the derivative is either 0 and it looks like this and it's nice and flat and you get your maximum or minimum, or you have a corner or a cusp and the derivative doesn't exist. Yeah, and those will be our candidates, and we'll come back to this in a second. So let's ask a question. A pretty natural question. Do all functions have absolute maximum and minimum values? We've just sketched two functions that have both, right? Do all functions have absolute max and minimum values? Do they have both, all functions? Pause the video, see if you can think about this and arrive at your own answer. So let's sketch some pictures. Pictures really, really help here, and it's nice to have an idea of all of these examples in your head whenever you approach the homework. So let's sketch a function a to b, but let's suppose it's not going to include the endpoints. In this case, I have a function that's continuous on the open interval from a to b. Continuous, CTS means continuous, on the open interval from a to b. But in this case, is there an absolute maximum value? There's not, it turns out. No matter what value you pick as the largest on this interval, and my b should be here, I guess. Sorry about that. No matter what you pick, suppose you think that this value is the largest on the interval. Because the endpoint's not included, there's always going to be a value that's slightly higher. It never actually attains a maximum value. Yeah, it never actually attains it. Same with the minimum. If you think that this point here is the minimum value, the function goes down even further on the interval. So there's actually no absolute minimum or maximum. And that's kind of strange. So if we're continuous on this open interval, the answer is no. It does not have to have an absolute minimum or maximum. Could it? Sure. Let's draw one where it could. What about this function? Here's A, here's B, and suppose here's my open circle, and it goes up and then down. Yeah? Does this function have an absolute min or maximum value? Pause the video, see if you can figure this out. The answer is yes. The absolute max is here, and the absolute minimum is here. These are both local mins and local maxes, right? But they're not guaranteed. This example says that they're not guaranteed. It could happen, but it's not guaranteed. What if we have a point of discontinuity? Let's draw another picture. Suppose we have nice filled-in endpoints that make us happy, and maybe we have a vertical asymptote. Yeah? Does this function attain its minimum or an absolute minimum or absolute maximum value? Pause the video, what do you think? The answer is no, right? it never attains the minimum value because this asymptote goes as far down as you want it to go, right? No matter what value you think is the smallest, most negative value, there's always one below it. Similarly for the ones going to positive infinity, there's no absolutely largest y value that it hits. So this function is not continuous on the closed interval AB, and again, has no absolute min nor max. But what if it didn't have a vertical asymptote? What if it was something a little bit more benign, maybe? What if it was just a hole? Does that hurt? And the answer is yeah, it does hurt. Let's consider the following function. Closed interval, closed interval. Let's do our favorite wiggle function, but maybe here it has a hole. So what's happening here? At the top, I certainly have an absolute maximum. And it's a local maximum, isn't it? It's an absolute and a local max. Yeah? But do I ever actually attain an absolute minimum value? No, because I've plucked out whatever that minimum value is. So if you pick any value, there's always one a little bit closer. Yeah? And let's zoom in. Let's make sure we're really okay with this. I'm going to zoom in on that hole there. I know locally, if I make it really big, it looks something like this. Yeah? No matter which value you pick, and again, I've zoomed in arbitrarily here. Yeah? If you think that this is the smallest point, there's always a point that's closer to the open circle, and that's really interesting. So there is no absolute or a local min on this function. There's no absolute or local min, but there is an absolute and local maximum. Yeah? So what function guarantees it? We've only seen one function that guarantees an absolute min and max, and it was these two functions, right? We drew two nice functions. What property do they satisfy? We're on a closed interval, yeah? We've seen the example. If it's not closed, yeah, if it's continuous on the open interval, we're doomed. But if you're continuous on a closed bounded interval, turns out you're okay. And this is called the extreme value theorem. If f of x is continuous on the closed and bounded, so it can't be the entire real line or anything. If it's continuous on some closed bounded interval, AB, here's my cat. She's a good cat. Then f of x attains an absolute maximum and an absolute minimum value. But it must be continuous on a closed bounded interval. Okay? And that's super, super important for us. All right. Let's look at some examples again. Let's see when this happens. And we've talked about this already. Let's revisit some examples. Consider the function that's going to be continuous on this closed bounded interval from a to b. And it will look something like, hello cutie, this. Pause the video. See if you can figure out, oop, that connects here. See if you can figure out where this function has its local mins and local maxes, and also its absolute minimum and absolute maximum. Give it a shot. All right, so we know that this will be our absolute minimum. This point here looks like our absolute maximum. And these are guaranteed, of course, by the extreme value theorem. This is a nice continuous function on a nice closed bounded interval. It's not differentiable, but it's nice and continuous. And we have a local minimum, or sorry, local maximum here at this little mountaintop here. And we have a local minimum here. Yeah? Good. Let's do another example. Pause the video. Where does this function have its absolute minimum, absolute maximum values? Where's where its local mins and local maxims? Give it a shot. So it looks like here we have an absolute max. This looks like our absolute min. And where our local minimums, we have a local min here. And we have a local minimum down here at this cusp. We also have a local max, this little mountaintop. Yeah. Cool. What do you notice again? So we talked about this at the beginning of the video. What do you notice at all of the local mins and local maxes? At this local max, I have a slope of 0, don't I? At this local minimum, we have a point at which we're not differentiable. We have a little corner there, it looks like. At this local minimum, I have a slope of 0. At this local maximum, I have a slope of 0. And at this local minimum, I have a cuspy thing, and that is a point at which we're not differentiable. Yeah? So we have the following observation. And this is true. If f of x has a local min or a local max at x equals c, then either f prime of c is 0 or the derivative does not exist. Yeah, so the cases that we saw up here are the only cases. If it has a local min or a local max, either we have a horizontal tangent line or we have a place at which the derivative does not exist, right? Which could be corners or cusps or whatever, vertical tangents, whatever you like. But of course the vertical tangents, if it's, looks like this, will not be a local min or local max. Yeah, so that'll be something interesting that we'll talk about in a second. This motivates something called a critical point. Let's define a critical point. A point x equals c is called a critical point if this condition holds. If either f prime of c equals 0 or f prime of c does not exist. Yeah, we'll call that a critical point. That'll be a really important definition for us. Let's look at some examples. First, let's note a really important example. Just because the derivative is 0 or does not exist, this does not imply that the point is a local min or a local maximum. Just because you have a derivative of 0 or the derivative does not exist, that doesn't imply that you have to have a local min or a local maximum. As an example of the first, let's consider f of x equals x cubed. Then we know that the derivative of f is 3x squared. And if f prime of x is 0, that means that x is 0, right? So we know that we have a horizontal tangent line at x equals 0. But what's happening at x equals 0? You get nice and flat. I'm trying to make it flat. You get nice and flat here, but it's not a local min or a local maximum. It's not the largest, it's not the king of the hill. Yeah, it's not the smallest value in a little valley. It's kind of a saddle. This is going to be called a saddle point for us. Yeah, it's not a minimum, not a maximum. This is called a saddle point. And think about it like a saddle. If you could sit right here, right, and here's your little hands, you know, and you're riding your horse on the x-axis there. This is called a saddle point. It's neither a minimum nor neither a local minimum nor a local maximum. What's an example where we have the derivative does not exist? We're nice and continuous, but the derivative does not exist, and we're not either a local min or local max. Consider f of x equals to x to the power 1/3. Then we know that f prime of x is equal to 1/3 x to the negative 2/3. And we know that f prime of x does not exist at x equals 0. But what's happening at x equals 0 here, as we mentioned on the previous sheet of paper, you get a vertical tangent, yeah? So here, it's neither a local min nor a local maximum again, okay? Let's do some more examples. Find the critical points. I'm going to abbreviate, that's just critical points, of f of x equals x times the square root of x plus 1. Okay? Remember, what do we need to do? We need to find the places at which the derivative of f is 0 or does not exist. So pause the video, try to solve this problem yourself. Alright, so let's begin by taking a derivative. I need the product rule, right? It's the first times the derivative of the second plus the second times the derivative of the first. And what do I desperately want to do? I want to set this equal to 0, find where it doesn't exist. So how do we do that? We need to solve an equation. So let's factor this, yeah? Remember, the trick here is to factor out the biggest negative exponent. The biggest negative exponent that I see is x plus 1 to the negative 1/2 power. What's left over? In this first term, I'm left with a 1/2 x. What am I left with in the second term? I'm left with just x plus 1. Yeah? All right. So, let's simplify this. We get x plus 1 to the negative 1/2 times what? 3/2 x plus 1. And now what do we want to do? We want to set it equal to 0. So where does f prime of x equal to 0? It's where either this is 0, which can't happen because this is in the denominator, right? Or where this is 0. So really we want to set 3/2 x plus 1 equal to 0, which gives us x equals negative 2/3. Yeah. Where does the derivative not exist? It doesn't exist wherever we have division by 0, right? So where do we get division by 0? That's where this quantity, x plus 1, equals 0, which is, of course, where x is equal to negative 1. Yeah. Cool. And these are our two critical points. That's nice and easy, right? Let's talk about another idea. Suppose we have a function on a closed bounded interval and we want to find its extrema. We want to find extremas of a function on a closed bounded interval, continuous functions, of course. Well, where can the extrema occur? Where can our extrema occur? Let's look back at a previous problem. Where did the absolute minimums and absolute maximums occur in these pictures that we've drawn? We see one occurred at a local maximum, one occurred at an endpoint. One absolute minimum occurred at an endpoint, another absolute minimum occurred at a critical point, right? So critical points could be absolute mins and absolute maxes, and endpoints could be absolute mins and absolute maxes. Yeah? So if we want to find the absolute mins and absolute maxes, we need to do the following. We need to find all critical points. Yeah, because maybe we can't graph it, and that sounds hard, right? We'll graph later, but for now, if we can't graph it, we'll have to do this algebraically. So let's find all critical points. 2. Let's make a table. Let's evaluate f of x at all of the critical points and all endpoints. My cat's playing. I don't know if you can hear this. 3. The biggest of these values is the absolutely maximum value. And the smallest value is the absolutely minimum value. Okay? So, and this is going to be kind of the scheme that we're going to use for all of these problems. Anytime that you want to find the largest and smallest values of any function, as long as it's continuous on a closed bounded interval, we're going to find the critical points, and we're going to evaluate the function itself at the critical points and the endpoints, because those are the places where we can have the absolute mins and absolute maxes. The biggest value that we find will always be the absolute maximum value on the interval, and the smallest value that we find is always going to be the absolute minimum of the function on the interval. Let's see an example to see how this works. Let's find the minimum and maximum values of the function f of x equals sine x plus cosine squared x on the interval from 0 to 2 pi. Yeah, find the minimum and maximum values, absolutely minimum and absolutely maximum values of this function on the interval, closed bounded interval from 0 to 2 pi. So you have the scheme. Try to pause the video and find this yourself. All right, step 1. What's step 1? We want to take a derivative, right, and find where it's either 0 or does not exist for those critical points. So f prime of x is equal to cosine of x plus 2 cosine x times negative sine x, right? Here's our derivative. We want to find the critical points. I know that it exists everywhere. These are nice differentiable functions, so this is differentiable. So we just need to find where f prime of x is equal to 0. Well, so we need a factor. I see a common factor of cosine of x. So we have cosine x times 1 minus 2 sine x equals to 0. How do we solve this equation? We set each term equal to 0. Yeah, so either cosine of x is 0, or 1 minus 2 sine x is 0, which means that sine of x has to be 1/2. And remember, we need to solve these trigonometric equations only on the interval from 0 to 2 pi. So I hope you put your trigonometry hats on and remember how to solve trigonometric equations. So here's a good time to pause if you haven't finished the problem yet. Pause the video. Try to make sure you're okay with solving these two equations between 0 and 2 pi. All right, so where does cosine of x equal 0 in 0 to 2 pi? I know one of the values is at pi over 2, and another value is at 3 pi over 2. Sine of x is 1/2 whenever x is equal to pi over 6, or x is equal to 5 pi over 6. I probably don't need to do this discussion, but just to kind of jog your memory a little bit, cosine of 0 is where the x-coordinate on the unit circle is 0, right? So that's going to be straight up and straight down. That's pi over 2 and 3 pi over 2. Sine of x is 1/2 is where the y-coordinate is 1/2. So where's the y-coordinate 1/2? It's here at the angle pi over 6, and here at the angle 5 pi over 6. Yeah? So it's visually what's happening if you've forgotten. So these are our critical points. I have 4 of them. I have 2 endpoints, 0 and 2 pi. What does step 2 tell us that we need to do? I know that my absolute min and absolute maximum value will occur at one of these 6 points. So let's see what the function values are at the 6 points. What's f of 0? So we need to compute f of 0, f of pi over 6. I'll do them in order. F of pi over 2, f of 5 pi over 6, f of 3 pi over 2, and f of 2 pi. So, and now we just evaluate the function here. And the largest value is the largest, the smallest value is the smallest. So f of 0, I think, is 1. F of pi over 6 looks like, well, sine pi over 6 is going to be 1/2. Cosine pi over 6 is square root of 3 over 2. Squared is going to be 3 over 4. So this looks like 5/4. F of pi over 2, well, sine pi over 2 is 1. Cosine pi over 2 is 0. F of 5 pi over 6, we get sine 5 pi over 6, which is 1/2. Plus, well, it's negative root 3 over 2 squared, so that's going to be another 3/4 here to give us 5/4. F of 3 pi over 2 is negative 1, because sine 3 pi over 2 is negative 1. And f of 2 pi is again 1. So what's the largest value that you see? I see that 5 over 4 is hit twice at 2 different points. And I see that negative 1 is also attained. So what is the absolute maximum value? It's 5/4. And this occurs twice on the function. It occurs at pi over 6, and it occurs at 5 pi over 6. The absolute minimum value is what? It's negative 1. And where does this one occur? This occurs at 3 pi over 2. And I encourage you to use Desmos, graph the function sine of x plus cosine squared of x, and make sure that you see that it does attain these two y values, these two function values at these points. And these are, in fact, the largest values. All right, guys, so I hope that this helps, and my cat wishes you luck. If you have any questions whatsoever, please feel free to reach out, and don't hesitate to reach out via email. I'm happy to help in any way that I can, or we can set up a time to Zoom. And I look forward to seeing you in the next video. Thanks so much for watching.